Our guest speaker tonight is Dr. Emma Chapman. Emma has kindly allowed us to record this talk, so please keep the questions to the end. Emma studied at Durham University and gained a PhD at the University College in London. She stayed at UCL working as a postdoctorate researcher working on and funded by the Square Kilometre Array. She is now a Royal Society Research Fellow based at the University of Nottingham. She's among the world's leading researchers in searches of the first stars, where her work and her research with low-frequency array telescope, LOFAR, investigates the time in the universe when the stars began. In 2020, Emma published her first science book entitled First Light, Switching on Stars at the Dawn of Time, which is available.
You can hear it if you want.
Oh, well done. Good luck. Emma is a member of the UK-based research and campaign organisation that is dedicated to ending sexual misconduct in higher education. The group has contributed to a change in attitudes in this area. Emma has also won various awards during her career. Her talk tonight is entitled Searching for the First Stars in the Age of JSST. Please give a warm MSAS welcome to Dr. Emma Chapman.
Yeah, that's a great kind introduction. Can Zoom people still hear me? Hopefully, I'm getting a bit of sound from Zoom, so if I could just ask you to
Harry, can you
mute.
turn your mic off?
Everyone could just mute on Zoom. But welcome, Zoom people. Hello, Zoom people. Yes, so I remembered why I don't like giving talks at astronomy societies, because I came here early, chatted to everybody, saw your incredible radio astronomy group and the optical telescope upstairs, and realised I'm a complete fraud in comparison. So I feel like you can pick all the holes in my talk. But I am supposedly a professional astronomer, which means I get paid, whereas I don't know what I'm doing. Whereas you guys don't get paid, but you do know what you're doing. My talk is, I gave this kind of random title to it about a year ago, and I've just not changed it really. But what it is me having a lovely captive audience to talk about my interests and my research, and also just what I like to geek out at, but also trying to draw people in with the whole James Webb Space Telescope thing, because obviously that was a very big part of astronomy over the last couple of years. But I don't work with JWST, so I'm just going to declare that now. I'm using JWST a little bit as a way of trying to introduce you more to radio astronomy. So I'm using them as an infrared stepping stone, if you will. It makes it more palatable. We'll see. I don't mind questions during the talk, but if that is a problem because we're recording, then we can leave it to the end. That's fine. Yeah, so it's going to take me a bit of you getting used to this, because I'm used to pacing. So you might see me kind of pacing and then sliding back and pacing and then sliding back. There we go. Okay, so James Webb Space Telescope. I hear that you were actually part of the JWST outreach initiative here, which was incredible, where they gave you a jigsaw puzzle to do with the mirror and all sorts. They really had their outreach going. And they've had time to do it as well, because they spent decades building this machinery. Which I won't. Well, I mean, it's a beautiful machine, and there's even yeah. Look, you've even got where it is in comparison to the Earth, so I didn't even need to do any work today. But what it is kind of a successor to Hubble in kind of like a very rough way, in that it's got a bigger mirror, which means it's going to be able to see things with a kind of finer resolution than Hubble, with more power. But because it's an infrared telescope, it needs to stay really, really cold, which we'll get onto in a minute. But that's why you've got these huge sun shields here, each the size of a tennis court, trying to bat away all that nasty sunlight. And JWST was launched Christmas Day last year. No, 2 years ago now, I guess, so a year and a half ago. How many people watched it launch? Yeah, my friends. Yeah, so I don't know about you, but my Christmas Day stopped. I've got 3 young daughters, and they were all ordered to immediately stop with any of the battery related toys and get out. And I cried. Like, quite happily. I just welled up, and the minute it was safely declared to have reached where it needed to go above in Earth orbit, I was very, very excited to then see it head to its final destination in L2, and do so beautifully that actually it conserved enough fuel to last 5 years longer than they thought the mission was going to end up lasting. So they did a blooming good job with it. And then it was only 6 months of more nerve-wracking waiting until we got the first images, which in an unprecedented manner were introduced by President Joe Biden, who in a very short press conference, which I'm sure a lot of you watched as well, he introduced this first ever image from the Hubble, from the JWST, and we're going to go into this a lot more during my talk, because this is my bread and butter, is this kind of cosmological field. Now, I found this whole press conference really surreal, in that it was just American flag. And America has done JWST, yeah, and if you re-watch it, honestly, you can hear the words USA come out of his mouth about every other half sentence. Well, of course, it's a huge international effort, including ESA and everything like that. But it has been on American minds, certainly, which is why there was this big drive, because JWST has been trying to launch for almost half a decade. Basically, it's been behind in delays. It cost about $9 billion, up to $10 billion, I think, by the time it launched, which is not a small amount of money, as US Congress pointed out at one point. But as with a lot of telescopes, they argued that, well, you've already spent $5 billion on it, like, you kind of might as well keep spending, and it worked. And somebody said that it was less than the price of a bag of potato chips per American citizen in the end. So why not? But it was really, really nerve-wracking, because I'd certainly watched my whole career, watched this almost become a joke in my offices, because it was like, when's JWST gonna launch? Oh, next year. And I actually just remember this, I did radio for Inside Science Christmas special 2 years on the trot, just before this one actually launched, and both years they asked me to say what's going to be the highlight of next year, and both years it was JWST launching, and in both years it wasn't, and it took the year after, when I wasn't on it, for it to actually launch. So it was built with such incredible technology in terms of its folding mirror, which is almost like a dining table that folds up, and then these sun sheets that actually folded up from this tiny, almost like foil camping package that you'd take for an emergency blanket. And this was all on a rocket. And this untested technology, $10 billion worth, a career's worth of work, and to see it possibly explode would have been absolutely heartbreaking. So luckily it went up. And luckily we got these first incredible images. Now, these are quite dated now, which just shows you that the first time I saw this particular JWST image, I was absolutely floored. Now I can kind of look at it and be like, because that's how much it's kind of come on. And that last summer, where those first images came out just over a year and 2 weeks ago-ish, and then I had the most relentless summer of my academic life, where it was paper after paper after paper coming out. Almost every day there were new records set. Almost every day, I'm a popular science writer, and almost every day I had to rewrite what I was writing, because there was just older and farther galaxies being found. And it got to the point where by the end of the summer, I remarked to my partner, if one more paper comes out, I can't take it. Like, I need them to stop and give me a break, because it was just too much. But what they did was they did start producing this. This is an unfair comparison, as I'll get onto it in a minute, but in the same wavelength. So Hubble did observe infrared and UV as well as optical, though it was mainly looking in the optical. You can see what here is Stefan's context. So these 5 lovely galaxies, and you can see that with the JWST instruments, you can see a lot of different information. So these are particularly interesting in that you can kind of see these plumes of gas throughout the galaxies, and you can see just the kind of the bright nuclei of the galaxies there, whereas there it's just completely overwhelmed by optical light. Now, if we actually compare it to where Hubble has its strength, which is in the optical, then you could argue that it's that with an histogram filter on kind of thing, but it is showing you completely different information in terms of this is where your new stars are being formed, your old stars even dying. Whereas here you're really looking at the gas distribution, and it's the gas that feeds these stars and creates new stars. So it's been a great addition. And actually Hubble, it's still going. It's easy to forget it and think that it's been decommissioned, but it absolutely hasn't. And Hubble is still bringing out huge amounts of research. And it's got such a back catalogue of observations, like the Hubble Legacy it's called, that there's still PhD students going through Hubble Legacy data and finding new information. So certainly Hubble's not dead. But JWST is coming out with some quite astonishing things. So, for example, this is the Phantom Galaxy. And I personally think everything that comes out of JWST just looks nightmarish. I think it looks like the kind of place that like the Klingons would live if you were in Star Trek. It's like definitely they would live somewhere here, right? As opposed to somewhere in that nice optical happy place. So again, here what you're seeing in this Phantom Galaxy is that you're seeing mostly the gas, because you're actually able to get kind of through the dust that's around these stars, and you're able to really peer in to the stellar nurseries where you've got these really young stars being born. That's one of my favorites. And then it was Happy Birthday JWST about 2 weeks ago now, in terms of its first image. That's how they've decided to mark its age. And so they released this one, which is another corker of an image. Where you've just again got a lot of gas, but what you're seeing here is some really interesting objects. So here, for example, you've got a protostar, and it's in a cavern. So this is, if you can try and imagine it in 3D, you can kind of see it curving around here. But this is actually carved a bubble, which is going to be important for my talk. But it's carved a bubble out of this gas. It's really just ionized and burnt away all of the dust and the stuff that's stopping the light getting into that cavern. And so you can see that. But here, what we've got are jets of gas just coming out of this stellar region, just being produced and flying off. Which, if you try and look in the optical at a stellar nursery, did I include that picture anywhere? No, probably didn't. I might include it later. But if you try and look at a stellar nursery like this in the optical, then you can kind of imagine that this cavern just is covered in dust as well. You just don't see it. It's pretty rubbish. So the infrared, JWST has given us a lot. But this is the image that I'm going to be coming back to because I'm a cosmologist, allegedly. And so this is the deep field. Now, you'll probably be familiar, if you're interested in popular science, with the Hubble deep field as well. So that it was the Hubble ultra deep field, which looked almost identical to this, actually, which is why I was very surprised that they chose this image to be the first image, because actually, to the untrained eye, it looks almost identical to the Hubble deep field, and you could kind of be like, well, it's not that much better. But what is different is that whereas the Hubble deep field, it was on an area of the sky around the size of like half the moonish on the sky, and it looked like this. It's like, wow, loads of galaxies. What JWST did is then go into kind of one of those pixels, and this whole image covered a grain of sand held at an arm's length on the sky. So that is a grain of sand. So there are galaxies everywhere in our universe, to quite an intimidating extent, really, in that you just can't really pass it. You can't imagine how to see that around you. And it's a beautiful image. What was also different here is that whereas the Hubble Deep Field image took 10 days to produce, so 10 days of just staring at one place to wait for those very faint photons to get there. This one, they turned it on Friday, and by Saturday morning, they had this image. So this was the first image, and as they said, they went home, they had breakfast, they looked at what the results were, and this was there, which is absolutely astonishing. And what they chose to do was they chose to look at what's called a galactic cluster, galaxy cluster. So that's a really kind of tightly bound group of galaxies which all orbit each other, and they cause such a fuss when it comes to space-time, basically. The actual light itself is bent around it. So something behind that huge structure is that you can see it because the light is actually bent and magnified. It's nature's natural magnifying glass. And that's why we can see galaxies like that. You can see the arcs. And these arcs are all images of galaxies that are actually behind the main galaxy cluster. So much farther away, but we're managing to see them because they've been boosted and magnified. And this is the same galaxy. It's just that it's been distorted so much that you can actually see several images of it. This one is called the sausage galaxy. So they termed this one the sausage galaxy because, well, to get PR basically, but because it's been slightly squashed. And every time you look at this, I've just put this up on my wall in my living room. So I have it, I would say it's actual size, actually. I think I've got it this size on my wall. And I love it because I can look at it, and this is my favorite one because you can see really clear spiral arms. I'm really sorry, Zoom people, you probably can't see what I'm pointing at, but you can pretend and have a look at your own favorites. And then you've got this one that's got your really strong bar with just 2 spiral arms. And the fact that these are all on such a small area of sky that my eye wouldn't be able to differentiate it from the next tiny amount of dark sky is absolutely unbelievable. But this was one of their first targets in terms of what they wanted to look at, because it has the Hubble Deep Field caused such a furore when it came to cosmology. Nobody believed that there were this many galaxies out there. So when I forgot his last name, but Bob someone was the director of Hubble at the time, and he was given 10 days discretionary time. So because he was a director, he was like, you've got 10 days on the Hubble, look at anything you want. And what he decided to look at was completely blank space. And there was a lot of fuss over him. People were telling him he was just insane. He was wasting money. It was the Congress were going to be onto him. But he pointed at a dark point in the sky and he looked for 10 days. And an image like this came out where you've got all of these individual galaxies, which nobody believed that there were this many on that scale of the sky. So it's one of the first ones that JSST went for. Now, this breathless summer that I was talking about was because this image was publicly released. Most scientific consortium, when they have a big telescope, lots of people have done so much work that they are very reluctant to release open data, so data that anybody can access immediately. There's normally what's called like a period where everyone in the collaboration has access, but nobody outside. They chose to publicly release this, and what happened was that every astronomer with any free time basically went in here and started zooming in and picking out galaxies that they thought were the oldest ones in this image. And so what they did was they said, right, here's a really old one, there's a really old one, oh, I'm going to write a paper on that one, that looks quite old, and that one, oh, look at that one. And you'll notice I'm pointing out, the Zoom people, I'm pointing out all the red ones. And so you got a flurry of papers over this summer, several a day, from people that weren't even in cosmology, for example, just picking out red galaxies and saying that looks quite old, having a look at the kind of light that was coming from it and estimating how far these galaxies were away. Was that wise? We'll find out. Now, why can we do that? Well, it comes to it's because of light. Light has a finite speed, so we're used to it being very, very fast, but it's 300 million meters per second, very, very fast, which means that if you're trying to communicate, for example, with another galaxy, let's say you've got a friend in Andromeda, it will take 2.5 million years for your signal to get there. It will take 2.5 million years to get back, by which point, you know, you can't possibly be still alive, so you're very, very dead at that point. It's been 5 million years. You can't have a meaningful conversation with any kind of extraterrestrial civilization. And what we can extend that to is, okay, but what would they see today? What would they see if they are looking at us right now? Right, possibility. If they're looking at us right now, they're not seeing us. They're seeing light that's just arriving to them from 2.5 million years ago. So they're not seeing us, they're seeing the earliest ancestors of the human race. And they can only guess at what we've turned into 2.5 million years later. So this for our alien is a way of looking back in time. They can look back on Earth at that time and see these first ancestors of the human race taking their first steps, and they can see that happening. So it's not a simulation, it's actually that they're watching something happen in the past. And if we had a slower speed of light, the way it would work on Earth is that I could just point my telescope with some clever mirrors in the direction of Egypt, and I could watch them building the pyramids. So I wouldn't need to wonder how they built them. I just need to look, because the light would just be getting to me from 5,000 years ago if we had a much, much slower speed of light. So what we do is we flip this and we start saying, well, what if we start looking in directions and we start trying to gather photons that are just arriving to us from a time far, far, far in the past. And that's something called redshift. And so what we do is we just, this is my job, that's me. And what I do is I look at light that is just arriving to my telescope from 13 billion years ago. So it's been traveling for so long that when I look, I can see rough approximation, which I'm going to go into lots of caveats for the rest of this talk, but I can see the first stars, the first ever stars to be born in the universe. So I can even look further, actually, farther. I can even look farther and further back in time. I can see the darkness before using some fun radio astronomy. But what's happening is that as the light is traveling towards me over 13 billion years, which is a very long time, during that whole time, the universe is expanding. And when it's you can think of this in two ways. You can think of it as losing energy. It's like almost trying to run up a travelator, gladiator style, kind of like just trying to get, you're just losing energy. It's exhausting trying to fight against this expansion, basically. So you kind of go into the lower energy wavelengths of the light spectrum. But it's a bit more accurate to think of it as like, how do we observe it? And it's the same effect as when you're standing in a road and a police car whizzes past you. So this is the Doppler effect. It goes, and it changes pitch as it goes. So as it comes towards you, its sound waves pile up so that they are higher pitch. So that the higher pitch, you hear it higher. And then as it goes away, it's the sound waves are ever further from you. And so you hear it as if it is a much longer wavelength. And so it's this kind of thing. So because these stars are technically moving away from us because of this expansion of light, the photons from them continuously being pulled back, then they're actually, we observe it as if they're a police car shooting off. And so we observe them to be redder. And so this is what we end up observing, a much redder image. And this is why people just jumped on this image and went, that's red, that's red, that's red, that's red. And there's lots of problems with that. For example, you can actually just have a red galaxy that's really close by. So that's a problem. And you can also have lots of dust, which emits and scatters lots of red light. So you can have a perfectly lovely young blue galaxy, but if it happens to be in front of a slightly dusty galaxy, then you can have lots of effects there as well. But certainly the first ones went for this. So that's what we call redshift. Now, light is a spectrum, and you have all of these different wavelengths. It's a continuous spectrum, but what we do is we divide it fairly subjectively, really, into different categories according to the properties of the light. So we've got radio, which most of my audience will actually recognize this object. As one of the audience members who was at my work experience week at the University of Nottingham last week, I had to explain what this was and kind of instruct them as to the thing that their phone can do. It used to be just one machine called a radio, and before then a wireless. So this is a radio, and what it does, of course, is it receives radio waves that have been encoded with information such as the Archers from Radio 4, and you tune into the right wavelength and you can hear that even though it's from London or wherever it's being broadcast from. So radio is really good for long distance communication. It's very good at kind of keeping information in and not losing it. Now, infrared, the properties of infrared light are much more that it can basically infrared light is produced any time that you've got a hot body. So infrared, you tend to see, if you're not an astronomer, the only place you tend to see it is on COPS or some US show like that, where they're trying to chase people through a field. I've not really thought of many other, apart from actually when your remote control, when that's controlling the TV, you can see it. And if you want to prove that to yourself, you can take your iPhone or whatever you've got and take a video of you pressing the remote at it. And even though it looks like there's nothing there, because the iPhone doesn't have this IR filter, it can actually pick it up. And you can see the infrared that's from that. That's a little thing you can do at home. Then you've got your optical, which is this tiny slice of the electromagnetic spectrum. So, you know, me and the fellow radio astronomers were chortling outside at all the optical astronomers that commands the whole 300 nanometers of the electromagnetic spectrum. Then they managed to do a lot with it, so fair play. And then you've got the UV, which you see that in CSI a lot, in terms of black lights and all sorts like that. And then you've got your X-ray. And your X-ray is really good at being able to pierce through skin, for example, pierce through flesh, but it is rebounds very nicely from bone. So what you can see is you can get your X-rays. And actually UV, the reason UV is so harmful to us is because it cannot go so deep as X-rays, because UV light from the sun, for example, it can only go about, I think it's 3-4 millimeters into the skin. And so it stays there and it literally cooks you. Whereas X-rays do pass straight through your flesh and therefore do not cook you. Wear sunscreen. So you've got all of these different wavelengths here. And what we're doing with the cosmology is that we are not concentrating here, where kind of if you were just looking a little bit far away in the universe, you might go from, like, you might redshift, you might have a blue galaxy, I don't know, nearby. And that would redshift and you might see it a bit red. Actually, what's happening in cosmology when you're looking at something that's 13 billion years away is that it's redshifting through the infrared, where JSST is managing to pick up some really far galaxies, and straight into the radio. So redshift doesn't just refer to the red of the optical spectrum, it refers to the longer wavelengths, right into the radio. And yeah, this was just an excuse to show you some pretty JSST images in honor of its birthday, really. So these are actually probably my favorite JSST images, if I'm being honest. Not the cosmology one. I'm not even a planetary astronomer at all. They're just rocks that get in the way, so I normally don't care what they're doing. But when this came out, this just blew me away, seeing the outer gas giants with these stunning rings, and seeing Saturn not really take the podium for me for the first time. Whereas, if you know, in the optical, there is no don't start a fight, but there's normally no competition about what the most kind of, I don't know, emotional planet is to look at. It's normally Saturn. When you see those rings for the first time, it is life-changing, followed by Jupiter's moons for me. But yeah, in the infrared, it's a very different story, and what you can start to see is, for example, the aurora, so the northern and southern lights on Jupiter, of which there's a great radio experiment on your roof, which is trying to use this kind of aurora and the interaction with the Io, one of the moons, and they're actually trying to pick that up on the roof, which is I actually squealed when I came into the car park and I saw that experiment, because I've never seen one in the flesh. The only other person I know that's done it is Patrick Moore and Terry Pratchett, in terms of the people I've heard that have done it like as a home setup, as not part of a fully funded thing. So it's really, really cool. Yeah, and yeah, this was just my point, actually. This is the one I was looking for earlier, which is that in the optical you can have a nebula, which is a star forming region, and it can just be completely swaddled, really, in dust that you just can't get through an optical. But you take it with JSST, just goes away and you're straight in there to see the actual protostar that's being produced. And I can't see them on here. I think you need a better resolution, but they discovered that there wasn't just one at the center of this one. They discovered there's something like 4 or 5 when they undusted it, cleaned it. I'm not sure. I'm really aware that I'm waffling. When am I meant to finish? Is it 9.
Thursday,
Excellent. Count the beer. No. So this is a slide that I have stolen quite happily from the Open University because they have let me. It says so on their website. I really like it because it gives you just an idea of kind of the main events of our universal timeline. Obviously, it's not to scale in terms of time. And you've got the Big Bang. You've got all the kind of the first few minutes, first nuclei. You've got everything so hot, so energetic that nothing can form until about nothing that we would recognize like hydrogen or helium, no elements that we would recognize until 300,000 years ish after the Big Bang. And that's when suddenly you've got your electrons joining up with your protons, forming hydrogen, forming helium, and allowing the photons to just go on a clear path. It's almost as if you've got a penny at the bottom of a jacuzzi, you're looking at it, you can't find where it is at all because the light is just being bashed about everywhere. You just can't see. Turn off the jacuzzi, suddenly it's all clear. And this is just what happened about 300,000 years after the 380,000 years to be precise, after the Big Bang, was that the universal jacuzzi turned off, and suddenly you could start to see. And so we call that kind of I'll call it many things actually, but first light is one of them. There are so many first lights. I argued heaven not to call my book First Light, but I didn't get the final say in it. But if I was going to define it, it would be there. But then you've got the first galaxies and stars forming. And the reason this is happening now and not here is because it is so hot, it is so energetic, and these photons are really good at breaking things apart, as are the electrons that are flying around. So all you can do is hydrogen and helium. You can't build lithium or boron or carbon, and you can't build the first galaxies. To get those heavier elements, you need something to produce them. So you've got a universe that's just hydrogen and helium. And somehow you've got to get to the point where it's produced oxygen for us to breathe, silver for us to wear, carbon for us to make humans. And so that's where my research lies, is how did we do that? How did the first stars form? How did the first galaxies form? How did the first black holes form in this probably first billion years after the Big Bang? And about over a year ago, I would have given this talk and said that this is a completely mysterious time, as in we've never really had any observations from that time. So it really was an unsolved mystery what was going on there. We've switched JSST on now, and now that has managed to push back, and we've managed to start seeing some of the first galaxies, which I will go on to a bit later. But we're still not pushing any further back than that. So kind of this is the part where I'm like, yeah, come see a talk about JWST, and then I spend the entire talk trashing it, because it can only do so much. It's not the savior of astronomy. It is not the only thing that's going to take us through the next 100 years. And that is because of the limit of the light, of this redshifting that I talked about. So Hubble, it was mainly looking in the optical, which means that anything that redshifted out of the optical, it couldn't see. It was as blind as us to being able to see any of these objects that went deep into the infrared. And so it was able to see back to like some of the early galaxies, for sure, but not right back there. Now, JWST, because it's infrared, that was able to look a little bit further. So something from here that Hubble had tried to find out, it would have gone to these wavelengths. It's infrared, you just can't see it. It's just invisible to it. So suddenly, out of these deep fields, popped up a whole load of older galaxies for JWST, but it can only get to about there. So it's done a cracking job. But if you really want to get back to this era, the first few 100 million years, the dark ages of the universe and the first stars, you have to have a radio telescope like the Square Kilometre Array, of which I am supposedly a part of. And this is my existential crisis slide, and I'm happy I put this in actually, because I've had this crisis just in the last hour, having spoken to your radio astronomers and been like, I don't know this. So I am supposedly a radio astronomer. I've never fixed a radio antenna in my life. So I use antennas in Australia and I use antennas in the Netherlands, but if one broke, I would not have a clue. So supposedly called a radio astronomer, but yeah, it depends who I'm talking to. So for you guys, I'm going to go with astrophysicist. And I don't even know the difference between the words. Astronomer and astrophysicist. It's something I've tried to figure out for quite a while, but I think it's just that one sounds a bit posher. I'm not really sure. And sometimes I'm a cosmologist, but again, like when you actually talk to kind of real cosmologists, then they're really interested in the first few minutes and what happens before the Big Bang, and they get all philosophical of late night, and I'm just not with them either. So recently I've just been peddling myself as a historian with a telescope, because that's where I kind of come from. I was just talking to Sparky here about my kind of origin story, which is that I was interested in history originally, in unearthing this kind of lost time in terms of Egypt. And it was only when I got onto watching the X-Files and finding my heroines in Dana Scully and then Sam Carter in SG-1 that I was like, wow, science looks cool. I was like, well, how can I do these things both? And then I picked up a book on popular science book on special relativity about kind of looking back in time and time travel. It blew my mind so much that I just switched from history into physics in terms of my A-levels. And that's what it's about for me. So for me, it is that I found a tomb that is way older than 5,000 years and covered in way more dust than Egypt. I've got something that's 13 billion years ago and just covered with a mess of all of it. And yeah, I'm not going to be using first sources from the Rosetta Stone. I'm not going to be using that. For me, what I need to use is a telescope, because if you told any Egyptologist all they needed was a telescope to watch the pyramids being built, they would snap it up. And that's exactly what I did with this kind of area. So why do I care about these first stars so much? Well, partly it is that, partly it's that it's just unknown, and I don't like the unknown. I like to fill it in. I like all the gaps filling in the history. But it's also because they're very unique. So they're unique in terms of their compositions. So all stars are defined by the fusion that happens at their core. So they are lucky collapsed clouds of gas, which are so dense at their core that the very atoms that make them hydrogen are pushed together to fuse, to form helium, which in its way produces a huge amount of light and energy. Now, it's actually not a huge amount individually. So if you fused two hydrogens in this room, it wouldn't blow the place up. It would give you less energy than a Mars bar. But because there's a hell of a lot of it in the sun or any star, then overall it produces such a pressure that it holds back that constant crushing, inevitable doom, which is gravity. That's what defines a star. But when gravity eventually wins, which it always will, sorry, just had a lot of jokes about anyway. Yeah, so gravity always wins in life and in stars. But yes, so you end up getting gravity winning, and it pushes together these stars with such a force that it actually rebounds. They supernova, and they throw out all of these heavy elements that they've managed to produce, because inside they've been busily getting on, going hydrogen to helium, helium to lithium to beryllium, boron, carbon. They go all the way up to iron, so really quite heavy elements, before they just can't produce the energy that's being put into creating iron, for example. And so gravity begins to win, but they pollute the gas. So it's these first stars which are the factories for all of the heavy elements that we need to then produce the later stars that we see today, planets, us, etc. And this is another JWST image to again rationalize the title of the talk. And I really like this one because it's people don't know this one very well. But this is a star, and these rings are not a telescope effects. These are actual, almost, how would you describe them? They're puffs of dust. So this star is slowly dying, and it's contracting a little bit, and each time it's doing that, it's blowing out the outer layers of its, and what all of these are carbon. And so these are basically rings on a trunk, and you can tell how many years this star has been producing this carbon. And so this is actually a star being caught in the action, kind of polluting its outer atmosphere. I've never ever seen anything like that. So again, this is a JSST image that's little known, but I think very important. Now, as I just mentioned, the first stars, these what we call metal free, which basically means it's only got hydrogen and helium in it. Because as cosmologists, what we are used to is a Big Bang, which just produces hydrogen and helium. There isn't anything else in the universe. So what we tend to do as cosmologists is we have a periodic table, but it literally just goes hydrogen, helium, metals. And that's how we refer to everything. So metal-free stars mean just hydrogen and helium. These fuse some heavier elements, they supernova, pollute their atmosphere. That over about 1 million years or so will collapse again, and it will turn into what we call a metal poor star. So that means it's got a few heavy elements in, but we're still mostly hydrogen. And these are what we call population 2. So you might have seen some population 2 stars. There's plenty in our galaxy. And then these collapse, pollute again, and then you get your population 1, which are what we call metal rich stars, which are like our sun. Still only like 2% heavy element compared to hydrogen, but it's enough for them to define these 3 populations. Now this population, as you may have guessed, 1, 2, 3, population 3 are the first stars, the metal free stars that we have never ever observed. And they are unique because you cannot form them today, because there are no clean, pristine areas of our universe left that we know of. It is mostly, it's so heavily polluted over 13 billion years that you just can't produce them anymore. So it's useful for stellar astrophysicists as well to actually to find out about these first stars. It's useful for nuclear fusion people to look at these first stars, because there are so many physical theories being tested in this kind of early laboratory, if you will, of the early universe, which you cannot recreate now. So it's useful for a lot of different physics areas. And they were fun, they were massive. So we think they were about 100 times the mass of our sun, in general, even up to 1,000 times the mass of our sun. Now we do have stars that are that massive that we've observed, but they are rare, whereas it's normal. So the early universe was populated with these giants, these mammoths, everywhere. And they were, because of their size, they were very, very hot, which means they were very, very blue. So the universe would have been lit up by this kind of blue light in these first billion years. But unfortunately, there is a very clear relation, which is the more massive your star is, the less time it will live overall. And that's, even though it's got more hydrogen, more fuel overall, gravity in a much larger object is so much stronger that it crushes it, fuses its way through it way faster. So whereas our sun might last, let's say 10 billion years, we're hoping, of which we're about halfway through, a first star will have lasted about 1 million years only. That's nothing, that's barely any time at all. And to just kind of drive that point home, really, this is one of the timelines that I stole from Carl Sagan, in that he came up with this really interesting concept of describing cosmological time over a single Earth year as a way of being able to understand the rate of things, because saying billions, you're just not able, the human brain isn't able to really understand what a billion is compared to 1 million, which is why apparently we don't understand the inequality of poverty, etc., because we don't understand how much richer billionaires are than millionaires. But so if we say that at the strike of midnight on New Year's Day, then you, or 0000 on New Year's Day, you have the Big Bang, so everything begins, and the whole of January is basically taken up with forming atoms and everything like that. And the first stars appear on the 3rd of January, and they last 3 days. So they're dead by the 6th of January, I think it is. 3 days, the first stars are in existence in our entire cosmological timeline. And then you've got the rest of February, March, April, May, just making galaxies. So that's it. That's all that's going on. Lots and lots of galaxies. And then it takes to September before our solar system forms. October, you start to get oxygen. Can't really see it, but December, you've got your multicellular life. And then you have to zoom in a little bit, because then you have to be like, well, what's happening in December? Where are we? Well, you go to December and you get your Christmas gift of dinosaurs, 25th of December, aren't they cool? Everybody loves dinosaurs, but of course, 30th of December, we lose them all. So the dinosaurs are only in existence for 5 days before they're completely wiped out. Again, where are we? You zoom in again, you look at this final day, this 31st, and you've started to get people. And at 4 minutes to midnight, you start to get human migration across the globe. And then you go into your final minute and you're still not anywhere near us, and you've got all of civilization, and you've got China, you've got the Old Testament, you've got all this Columbus a second ago. And then finally, we've got revolutions, war. Yeah. And then you and so I present this for 2 reasons. The first of all, which is, as a cosmologist, I think it's important that we understand just how big the universe and how old the universe is, but also to show you that we do have something in common with the first stars, which is that we were gone in the blink of an eye in terms of cosmology. They were not important cosmologically in timeline, but in terms of what they did for the universe, producing all those heavy elements, nothing could have come after them if they had not begun to fuse. None of this. It would have remained dark and empty forever, because even with your dark matter below it, dark matter can't form anything because it can't lose enough heat and to collapse. It doesn't interact with light. Dark matter can't save you. You have to have the gas forming stars. So you get through this timeline, and there's these 2 reactions that tend to happen. The first is what I saw in a couple, which is just pure shock. You're just like, how am I that small? Like, it's just insane. And then you get on to the next one and you're like, why did I pay my mortgage for 30 years? I'm nothing. I'm no importance whatsoever. And I find this area really fascinating. People tend to have 2 reactions to this kind of information. One is those which is just a panic of the existential crisis. And so it is to remind people that you are young and you are small and you are incredibly rare in the universe. So in terms of kind of life, just live it as if you've already won the cosmic lottery, because you absolutely have. You live in a time when life can form. You live in a time when Saturn's rings are inclined so that we can see them. You live in a time where we're not being ripped apart by Andromeda. And that's the second kind of reaction that I get from people, which is that doesn't really matter if I eat the cake. Doesn't really matter if somebody broke up with me. It's like, and that's it. So people tend to be in 2 different camps, and it's the freedom of knowing that, which is quite nice. But in terms of the talk topic, we have to look back in time if we want to go back to our real beginnings, and we do that with the radio light. I'm just going to speed up a little bit. So you've got an amazing radio setup here. If for any reason not been round it because you've been dazzled by the big dome, go look at the weird looking things on the roof that looks like they've been left by Sky TV, because what they're actually doing is looking up they're actually managing to map the spiral arms of the Milky Way, even though it is just a dish. That's well, I love it. But anyway, radio can tell you something completely different. So here you've got an optical galaxy. There we go. So I couldn't find it. Optical galaxy, lots of dust. Looks like an average galaxy. Look at it with radio, and suddenly you've got these huge plumes coming out of them. And these are called jets and radio lobes, and they're common to a heck of a lot of galaxies. And what they are is a black hole lives here signpost. And you wouldn't know that from the optical. But because you have these jets, and because we've worked out that the only thing that can power something with that much energy to actually eject it that far from the galaxy, it has to be a black hole. So we know that those are within it. And we can map, I've already kind of gone through this, but we can map the different ideas. So optical, it kind of looks smooth, but you look in your infrared and you start lighting up your star forming regions. You look in the H1 and you start really tracing the ground structure of the spiral beneath it. And something like this, which is another JWST one, this is the cosmic eclipse. as it's called. And the reason I show this is because it's very vital for my research, in that what this is that is a very, very zoomed in part of a star forming region, of a star way up there off the image. But what has happened is that it is actually ionized or burnt away, or like just knocked hydrogen apart. So the electrons flown away from the proton. So it's ionized the hydrogen. What this is the edge of a massive spherical bubble in space. And every star does this. Every star produces so much radiation that basically nothing can survive in terms of hydrogen around it. And so you get a very different distribution in terms of what you're looking at. Very, very pretty. And so it is with regret that I then move on to the kind of images that we are looking for in my career from radio astronomy. And this is why so many people understandably move into optical astronomy, because it's very intuitive. We have been practicing optical astronomy since those first ancestors started walking and looked up and wondered whether they could eat the moon or something like that. You know, the lenses in our eye are everything we've done in terms of building optical telescopes. Radio, as I was just saying to one of your members, radio is we're the only animal that has managed to evolve in a way to see radio light. So you've got dolphins, which can disturbingly see an X-ray. You've got snakes that can track you in the infrared. You've got birds that can see in the UV. Nothing on Earth can see in radio light apart from humans. And that's because we've evolved to create our own eyes, which are those instruments that you see on the tops of the roofs, those antennas. It's only with those, and because that technology is so different to your eye, it's very easy to dismiss. It's very easy to say those images look rubbish, but it's because you have not got millions of years of evolution behind your understanding of that light. That radio light is just as powerful, and we're the only ones with access to it. So what I'm doing with my research is I'm using radio telescopes to gather that very faint light, and I'm doing it with something called 21 centimeter radiation, which if you just looked using the antenna on your roof, what that does is it picks up the 21 centimeter wavelengths. It's got a wavelength of exactly 21 centimeters. Only hydrogen really produces photons of exactly 21 centimeter wavelengths. So you tune your radio not to radio 4, but to 21 centimeters. And if you're looking close by, you see the spiral arms of the Milky Way. If I aim my telescope at a patch of the sky and I leave it for a very long time, and I mean it's been going for 10 years now, my experiment, and gather the faintest of light coming towards us, then what my 21 centimeter photons are doing is that they've been redshifted. They've been redshifted so much that I'm using a telescope that gets them at 2 meters. So I'm using a 2 meter setup to gather these 21 centimeter photons. And in the very dark ages, really like 13 billion years ago, all you can see is 21 centimeter radiation. So that's because you've got all this happy hydrogen, lovely and intact, all building everywhere, everywhere. And so if you optical eyes, you'd see nothing. It'd be black as anything, boring. Radio eyes, you switch them on, everything would light up and you'd just see it everywhere. And so we would just see just that basically. But then you've got your first stars turning on. And what happens is that they create these bubbles, which I've shown to you in the JSST images. They ionize that surrounding hydrogen. They knock away the electrons from the photon. So suddenly they can't manufacture those 21 centimeter photons anymore. So you just get gaps. And we call this the Swiss cheese model for obvious reasons, because these first stars make it look like a slice of Leodama, basically. And so we do this over the billion years, and we watch these bubbles getting larger and merging and changing shape and getting smaller because they're starting to recombine. And what we're trying to do is create a home movie of our universe over this 1 billion years where we're actually watching this happen. So I cannot stress this enough. This is not kind of seeing something locally that looks like it was 13 billion years ago. We are watching the universe begin to create the first stars as soon as we see these circles. And then as we go a bit closer, we are watching the universe begin to create the first galaxies because they produce a different kind of bubble, a much wispier bubble. So by looking through this time, that's what we hope to see. So yeah, you know what? Not as pretty as the JSST stuff. But in terms of being able to use what really does look like just a metal antenna, I can even show you actually, there you go. That's what I'm using. And that can look back 30 million years. Like, that's why I fell in love with radio astronomy, because optical astronomy is not easy, but that getting that to look at the first stars, that's next level for me. So we've got 1,300 of these all joined up, all looking together. And then we are currently just beginning construction on the square kilometre array, which is 130,000 of what we call Christmas tree antennas in the Western Australian desert. And those 130,000, we're linking them up. And those are going to be so powerful that we are going to be able to produce those images over that lost billion years, and watch a scary time resolution. You know, this movie is so big that it's actually we had a meeting with Nvidia last week because our hard drives are melting with the expected data rate that's going to come out of this telescope. So Nvidia are working with us to create better cooling systems so that our hard drives don't explode. We're working with fiber optic companies because they cannot build cables that get the data rates fast enough for our telescopes. We're having to delete data on the fly. And oddly enough, because all of the solutions are costing so much money, currently the cheapest and the best way of transferring data for this is actually to download it, let it come in onto a hard drive or a CD and send it on a plane or through the post and get it. That's the quickest way of transferring this data at the minute. Bizarrely. Yeah, and so JSST, just a quick last couple of slides on the last few days, really. This was a couple of months ago, this one, but this is one of the oldest galaxies that JSST has managed to find, because this is called the Cosmic Tomato, and it is a galaxy 400 million years after the Big Bang. So really, really one of the earliest possible galaxies out there. And what's very surprising to us is that it's huge compared to what we thought. So it's about 125 times smaller than the Milky Way, but for something that young, it's way too big for what we thought was going on. Like, we should be looking at the first stars at that time, not the first galaxies. How they have managed to form galaxies by that time, really big mysteries. And in the last, this is 17th of July, so a few days ago, somebody suggested that actually maybe these red blobs that we're seeing, that people jumped on so quickly and said, this is an early galaxy because it's red. Maybe it's something even more interesting. Maybe it could be dust, but maybe it could actually be a failed dark matter star. And I could talk a lot about why even describing these as stars are completely wrong, because they're not fusing. But what they are halos of dark matter, which have collapsed enough that the dark matter might be annihilating and creating some light through that annihilation process, which would then come out. So this is very, very, very kind of like edge of science stuff, but it's really, really interesting. And there's also been research in the last couple of days as well, which people are claiming that because of this mystery, where this is too big, like what's going on, either we don't understand galaxy formation, or the universe is a lot older than we thought. But I'm presenting these two because these are the theories that are coming out in kind of the popular culture. But what we have to really remember, and this is the sensationalism part of my title, is that even the scientists have got overexcited with this. And actually, the scientists have got more overexcited than the public. The public are more skeptical than a lot of the cosmologists I've seen that have jumped on things just because they're red. And so it is worth remembering this is very early data still. They're still figuring out this telescope. We've never looked this far back. So treat everything that's coming out of Webb, and to be fair, everything that's coming out of the radio telescopes when they start producing their real data in a couple of years, when SKA turns on, with real skepticism, because there is a lot of sensationalism, there is a lot of clickbait. Webb is not the be all and end all of astronomy. It is but one part, and to really go that far back, you do need something with radio. And I'm going to end with some holiday snaps, just because I put these in quickly just to show the radio astronomers in the group. But this is why I squealed when I came into the car park and tried to identify all the different individual experiments, because I collect radio telescopes like other people go around the world and collect cups or spoons. Whenever I go somewhere, I look up where the nearest radio telescope or nearest deep space NASA antenna is. So I went out to California and found there was a deep space network one there, and I managed to see it tracking a lunar mission. I drove 4 hours in a terrifying rental car north of California and visited the Allen Telescope Array, which is looking for signals from SETI, Search for Extraterrestrial Intelligence, which is my sideline. Jodrell Bank, if you haven't been there, honestly, you have no excuse. So get yourself down there. And then this was me last year. I know, right? I know. So this was my pilgrimage. This was my Mecca. This was my pilgrimage, because this is a 300-meter, that's 0.3 kilometers diameter radio dish with its receiver up here. So this beautiful instrument managed to use radar to map the surface of Venus and Mercury. It discovered ice, water ice at the poles of Mercury. It's looked for SETI signals. It sent out the Drake signal that is on the t-shirt. that signal was sent by this telescope in 1970 something. Unfortunately, it collapsed, as you can see. But when it did collapse, and you know why? Having been out there and interviewed a lot of very bitter people, is it collapsed because it was not taken seriously as the optical experiments in the national observatories of America. So they didn't fund it for years. For years they warned them this was going to happen, and they let it happen because it's just radio. Can you cut that bit? I've just realised I'm being recorded. But anyway, you get the idea. Allegedly. Yeah, so this was anyway, but leaving you with an actual radio image from the preliminary square kilometer array, which is called Meerkat. This is the center of our galaxy. We are now at the point where we're producing images that our brains as optical Neanderthals can finally understand. And there's a hell of a lot in there. There's magnetic filaments, you've got supernovae remnants, you've got Sagittarius A, which is the black hole. I don't think the runaway pulsar's on here. There was a runaway pulsar somewhere. Yeah, anyway, radio is awesome, and I wrote a book, so feel free to. I have some copies if you'd like to buy any. I even have a little packaging. Yeah, people like it, so yeah. Thank you.